So, and let's move to the cross project part. And the last time we only solved the task 2 and 3. And today we will solve the task 4 and task 8. Firstly, let's see the task 4. And we need to analyze the channel series condition. What is this condition? Which means we need to compare the source data rate and its will less than the channel capacity. And we need to add the following calculations to program to develop for task 2 and task 3. First is the channel capacity without noise, and second is the bit error rate for the specific signal noise ratio and modulation tab, which let me see here, which mentioned in your course project here, your signal to noise ratio and modulation tab here. So everybody should have their individual parameters. Come back to here. And the third task we need to calculate the channel capacity with noise, and we need to make a conclusion of whether channel theorem conditions is met or not, and based on your calculations. So let's see what is get nice for the task 4. And so we need to use the following equations, and here the tau is the binary symbol duration, and we already specified in this task 3 tau, and here we already specified here, and we need to calculate the error probability of our specific modulation type, and here the probability errors formulations as the this function, which means the energy per bit to the noise power spectral destination, and how can single noise ratio already specific, so we can calculate the here probability of the error functions, and now we will use here this to calculate the error probability for the different modulation types. And it's already explained in the lecture, and why they have different efficient constant. And we need to calculate the channel capacity with the noise, and well, it's binary channel capacity with noise, and it like this here. Yes, here use this the logarithm properties, this function. And here has the Laplace function in octave, and ERF function can be used like here. And so for the Laplace function, also remind here. And so the idea was we need to get the x variable of the Laplace function. Then we need to put it inside this function, ERF function. Then we can calculate the error probability for the different modulation types. So let's move to the octave. And last time we already calculated the task 2 and 3, and I will keep it safe here and use the split code to the split different task, which is the task 4. We need to calculate the noise channel capacity, and we only need the tau is enough. So and the binary channel will be the 1 to the duration, symbol duration I already specified here, TSYM will be the noise channel capacity. And we still need to specify the single noise ratio, and in the Dr. Ina's case, it will be the, let me check this, signal noise ratio will be the 12. Let's do it. Yeah, it's already very specific here, and we need to calculate the signal noise ratio linear function and use here. Calculate this part. So EB will be the, let's see, this function, and the power of the 10 power, the power of the signal noise ratio over the 10. Yes. And will be the signal noise ratio. Yes. And we need to calculate the square root of the single noise ratio, which will be only, this is the particular case in the BFSK modulation. So we specified it will be the X square with EP. That is the in the ERF function. So we can calculate the probability, error probability for the BFSK. We'll only use the, so Laplace function. We will calculate here and use the 1 minus the Laplace function. And 1 minus, this part will be the Laplace function, and 1 over 2. This part which means the x or 2. That is the error problem for the BFSK modulation. And we can calculate the channel capacity with the noise. So let's firstly check it with the error probability, which will looks like here, and it's around minus 0.5, and we can check it. Yes, here, which is the BFSK. Yeah, here our signal noise ratio is the 12, and the BFXK around yeah, close to the power of the minus 5 between here, this point. Yeah, that is correct. Now we can calculate the channel capacity here, and is 1 plus the, which will multiply the log 2 here plus to the 1 minus BER log with. Then we use the total of them to divide by the symbol duration. And it will be the channel capacity. That's right. And well, you will see the channel capacity with the noise. It's very close to the channel capacity without noise, and so the bit error rate is, how to say, not very low here. However, it still can achieve good performance here. So, and the data rate, which is our data rate here, our data rate is smaller than our channel capacity with the noise. And you will see here, this is our data rate, and this is our channel capacity with the noise. So we can say it meets Shannon's limitation conditions here. And however, you can, according your specific results, to make your own conclusion whether it meets the Shannon's theory condition or not. And the next task is task 8. We need to evaluate the probability of the more than 2 errors per code word with the specific Hamming code word length and calculate the bit error rate. So first is our specific Hamming code length, and it's also given in your individual parameters. Let's see. Here. This is our error correction code parameter, which is our code word length. And in the Dr. Anna's code word length case is m equal to 7. So let's move to the gain lines of the task 8. And the probability of the 2 and more errors per code word length, m bit, which means m code word length or non-code word, m bits non-code word. So we use the generalized formula, and p error, probability of the error, which we already calculated in our case. And yes, here. And we also need to note that the Hamming code for the correct the errors, we only can correct one error here for the Hamming coding. So, and this is a generalized formula. And let's see what the component it has. And first is the p uncurl of the in the in the 2 and more errors probability for the proposed word mass. And one, that is our source maximum entropy, source maximum entropy in the binary channel, capacity in the binary channel capacity, which will be the, that is 1. So, and this part, which means the no errors. Yes, we use the 1 minus error part, and m. So here the m is the our code word length we already get from our individual parameters here. So that is m. So, I mean, not 1 is 7. Seven bits code word. Seven bits code word. So here will be the 7. And for the Hamming code, we only can correct one error. So that is the sum function, just animate, because we only can calculate one errors. So here will be the I from the 1 to the G. So, and our G is 1, so we only can get this for the C7 1. That is still equal to our M, which means our code word length. Then we can calculate this part, which means the one symbol with the arrow. So it will be the P arrow I equal to 1, and one symbol with arrow. And this is the one symbol. Yes, one symbol without arrow. One symbol. without error. And I equal 1, m equal to 7. So we can rewrite as the probability of the uncorrectable error will be the 1 minus and the 1 without error and the minus 7 here. That is the m with 7, and will be write as the m, just the white number here. Is the 7 will be the p error, and one symbol without error. So p error here, that will 7 minus I will be the 6. Now we can calculate the probability of this part in octave. So it will be the task 8. So yes, B. We need specific the hand coordinates equal to 7. That is coordinates. And the probability of the incorrect will be the 1 minus 1. And the power of the 7 is the m. Yeah. And m multiplied with the yeah. The one symbol without error, that will be the here. So let's see the probability of it will be the probability of 2 from. So you will see the 2 or more coordinate error. That is quite lower than the here. So we need to here, which will be yeah. So it's done. We finished to calculate this part. That's all for the task 4 and the task 8. Let me stop share. So, Dr. Alice, are you here? Okay, he is not here, so almost finished today. And thank you, everybody, and see you next week.
Thank you, sir.